Hello, my name is Rajesh Munavalli. I'm a distinguished data scientist at PayPal. Today I'll be talking about how to build state-of-the-art chatbot when you have limited label data. Today's presentation is part of our work in implementing an in-house chatbot for customer service. We had two solutions for our chatbot, one using IBM Watson and the other developed in-house using deep learning techniques. So if you're using a third-party vendor like IBM Watson for intent prediction model, it will be a black box and will only have limited ways to improve the model. So you will have more options if you have your own modeling infrastructure. So most of the talk here would be quite relevant to the in-house models where you have more control. So here's the agenda for the talk. So I'll start out with making a case for why we need large amounts of label data, and followed by two primary solutions. One will focus on generating more label data, while the other will focus on modeling solutions to overcome label data limitation. After that, I will show results from our experiments as well as highlight what worked and what didn't. I'll also point out to our future research direction. So the first question we need to ask is, do we even need supervised models? Can I just get away with unsupervised models? There are a few things you can do using unsupervised models like topic modeling, clustering, etc., where each topic could map to one of the intents. Right? However, they have a lot of limitations for practical use cases. Supervised models outperform in practically every aspect. While they promise great performance, but it comes with a cost. The models are quite complex. Most of them have hundreds and millions of parameters. So for example, BERT model large has about 345 million parameters, and even the small version has 110 million parameters. So as you know from your experience, typically the data requirement is proportional to the complexity of the model. So the more complex a model is, the more training data you would need. So roughly you would need 10x the number of parameters in the model. So apart from the complexity of the model, natural language understanding adds additional complexity because of the way natural language is ambiguous and needs context to interpret the same words and sentences. There's a lot of subjectivity when it comes to labeling the data. In our case, when we asked 3 subject matter experts to label our intent data, the agreement rate was roughly 65%. So that means even humans don't agree on 1/3 of the data. Then there is also a question of granularity. So intents or topics can be very vague. Some are well defined and narrow, but most are usually ambiguous. Add polysemy and coreference to this mix, and you have even more complexity to address. And this is what we need to model when we are building an intent prediction model. So now that I have convinced you that you need a lot of good quality data, good quality label data, let's look at some of the solutions. So how do we get more label training data? So here is a chart. There's a wide variety of solutions. On the left side, you have a supervised approach, which requires a lot of human effort, and all the way to transfer learning, which is practically no human effort needed. And then there are some solutions which are a mix of human effort and modeling techniques to reduce that human effort as much as possible. So in this talk, I won't be able to cover everything. I'll try to give a very high overview of possibilities while focusing on some of the topics which I have highlighted here in red. So let's look at the two methods on the left, which is the active learning and the supervised learning. So the goal of active learning is to reduce the number of samples needed to be hand labeled for optimal performance. Not all labeled examples are important for building a classifier. So most of the approaches under active learning focus on how do we sample these data points. So uncertainty sampling is a technique to sample a data point for which the classifier is least confident about. So if you look at a decision boundary of a classifier, it will be the region which is somewhere along this boundary which we feel is the most uncertain. So another option is to look at what we call margin sampling, where you take data point with the least difference between the top two label probabilities. So in the case of intent prediction, typically you have hundreds of intents to classify. So in margin sampling, you will be focusing on the top two intents ordered by their probabilities assigned to them by the classifier. So in query by committee, we keep a set of classifiers trained on different views of the data set, and then we pick a data point for human labeling based on which data points have the least confidence. So in semi-supervised methods, unlike active learning, it's the opposite. So you take the data point predictions with the highest confidence and add them to the classifier and retrain the model on the expanded label data set. So self-training uses a single model, and you iterate over unlabeled data set to label until there are no new data points to label. In a multi-view training, instead of a single model, we have multiple models either trained on different features or different data, and then use the most confident samples from multiple models. Self-assembling is very similar to the previous methods, but unlike multi-view, in this approach we use a single model with different configurations. So think of this as a adversarial training, where you generate adversarial examples to train a model. And last but not the least is the generative models and EM framework, where you can use to generate more label data. So all these methods, however, have limitations in terms of diversity in the labeled examples, and they highly rely on your initial set of labels used to build your base models. So we can also look at similarity-based label expansion. So one most common way is using vector space model, where you have cosine similarity define samples which are very near to the labeled sample. So you take an unlabeled example and find the cosine similarity, and almost like a k nearest neighbor, you take that as a label for the unlabeled data. There are other ways you can do, which is given by the topic modeling, where again the idea is you have sentences belonging to the same topic must also have same label as the majority of the labels in that topic. So you can combine these two methods with active learning as well to label clusters of sentences instead of individual sentences. So LDA is a popular method for topic modeling, which works really well with documents which are of larger number of sentences. However, as you know, in chatbot, the user sentences generally tend to be very short in the context of chatbot. LDA does not perform well on short text. So instead we use a modified version of probabilistic graphical model, which is called bi-term topic modeling, which is based on a word-to-word co-occurrence across the corpus instead of the word-to-document co-occurrence pattern. So there are a few challenges with applying these similarity methods though. The one problem is same topic could belong to different intents, because topics themselves are at a very high level. And also on the other hand, different topics could belong to the same intent. So this will introduce a lot of noise. And in the next few slides, we will see how we can overcome these challenges. So you can use any of the techniques we discussed before to construct a bunch of weak classifiers and combine them to come up with a robust model. So Snorkel is a very good tool for such a task. Snorkel framework allows you additional ways to generate data using, say, a data augmentation like sentence shuffling or a WordNet based expansion, where you randomly pick a word or a verb or a named entity and replace with a sample set of similar words. Once you have a noisy labels from these different methodologies, Snorkel then leverages a generative model to combine labels from multiple sources and assigns a probability to that label. Depending on your tolerance, you can set a threshold to these labels above a certain probability and take that as a label data set. All these methods which I have mentioned so far, as I mentioned earlier, these are highly dependent on the initial label data set. And this poses a problem with the diversity, because if you only have a very handful of these label data set, there's not much variety in when you expand the data set. Otherwise, you have to add additional language complexity to get there. So in the next few slides, I will be focusing on modeling techniques instead of data generation technique. So all the methods I talked so far are all about generating more label data. So if you have a third-party vendor where you don't have much control over the modeling technique, the previous methods are the only ones you can use. But going forward, what I'm going to discuss are methods where you have much more control on the modeling technique itself rather than just generating more data. Of course, you can always generate more data from the previous methods, as well as do a modeling technique to come up with a much better model. So transfer learning is a technique where you learn a language model on a very large data set, which can then be used with a smaller label data set to achieve much better classification accuracy. So languages has same structure irrespective of the domain, right? There are many things which are common to your domain, and language is usually domain agnostic. There are some aspects of language which rely on your domain, but on an average, you can, it's the same language. You don't have to know the domain specific language for majority of like 99% of the words on the sentence structure. So here what you do is you train a model on a very large data set, and typically you train these on a open source data source like Wikipedia or books corpus, and BERT is one example where it was trained on close to like 3.3 billion words, out of which like 2.5 billion were from Wikipedia and about 1 billion from book corpus. And in BERT, they focused on the masked language modeling. We're basically given a set of words in a sentence, and you randomly mask any of the word. Can you guess what that word would be if you're given the other words, right? So basically you're given a context, can I guess what that word could be? And the second task was, given a sentence, can I predict what the next sentence would be? And both of these are unsupervised techniques, and hence you can train on a much larger data set. So once you have this BERT model, which is trained on a larger data set, then you can leverage that data or model to fine tune on your handful of label data set. So the pre-training on a larger data set is not just limited to just a one time. You can keep on fine-tuning it to fine-tuning any number of times. In our case, what we did was we took BERT and then we did one more unsupervised training of BERT model on PayPal corpus, and then finally we fine-tuned it on the very small label data set we have. This helps with the word context much better. For example, the word CC, which means credit card in PayPal domain, but in general use case, it might just mean like email carbon copy, right? So if in the general corpus, if it has learned as carbon copy, but it might have also heard about CC in the context of some of the financial related documents as credit card. But with one more layer of pre-training, what we are giving the model is more context around how CC will be used in PayPal domain. And what we saw is with this additional training, we saw a huge improvement in intent classification. So there's another way we can look at the training data. Luckily, in at least in our PayPal use case, I'm sure it might be true in other use cases as well. The intents have an inherent hierarchical structure. So, for example, here, the word dispute might have did not receive an item, or maybe a wrong item, or maybe general question and dispute. So, what we can do is we can use the word embeddings or the class hierarchy using different architectures. So the idea is that the goal here is like parent node will always have more training samples compared to a child node. So if there is a lower classification confidence, we can narrow down to disambiguate within the smaller set, within the subtree, rather than searching through the entire set of intents. So this is another way where you can also think of a multi-class classification for the experiment. So now to the main question: how did we do using all these techniques? Right. So here are the experiment results. There are a few surprises. So one surprising result was that weak supervision labels did not actually improve the model. When we dig down, it looks like we added more noise than quality samples. So that could be the reason. And another surprise was transfer learning outperformed all the methods. And with the domain-based retraining, we could further improve that model significantly. So the BERT model, even though you might have trained on a domain-specific data, the larger context of Wikipedia and book corpus actually helped. Even with the base BERT model, we could achieve like 75% compared to in-house model, which were about 74.8 with domain pre-training as well as high quality data. So some of this could be to the transformer architecture, but I feel even the larger language modeling context provides a lot of lift in performance. And if we apply the domain pre-train to the BERT model, we see that the performance goes all the way to 82.4%. And if we use the hierarchical models, then it even further improves the parent node level performance to 86.3. So the what we call as a supervised modeling paradigm, right? So what if we completely abandon this notion of supervised and instead go for reinforcement learning? So for our future research, we are looking at these model techniques where instead of relying on a labeled data, we modify the learning policy to be a learning on a reward function or a penalty function. So reward function could be something where you completed a conversation successfully, and it's a penalty or a negative reward if the conversation ended up transferring the chatbot to a human chat. So the model here continuously learns from failed conversation without human involvement, And this is an ongoing research and hope to share the results soon. So we are very early in that phase. I hope this talk provided some ideas which you can use in your own models. And I thank you for your time. And please let me know. Please reach out to me if you have any questions. Thank you.